we had some lectures by, evening lectures by Professor Balakrishnan. I'm sure that you must have heard of him. Now this question always bothered me, and every time I went to the class I was afraid that I had no clear picture of this. In my case, my attitude has always been that acquiring knowledge is incremental.
Okay. So, hello everyone, welcome to this exciting session set up by the Physics Club of IISER Bhopal. Today with us we have Dr. Subhash Chaturvedi, here a professor at the Department of Physics here at IISER Bhopal. His work specializes in quantum mechanics, quantum systems, and he has done revolutionary works in the fields of theoretical physics. And hopefully after this interview we will get to know more about Sir and get some insightful information from him.
All right, thank you very much for interviewing me, and this is the first occasion that I am being interviewed with camera, microphone in front of me.
Okay, so I'll go with the first question that we have for you. Okay, so sir, what has inspired you to choose a career in physics primarily?
Yes, before we begin, let me clarify that the what was said in the beginning, that I have done some very revolutionary work, is simply not true. I have done what I could and what I liked. So I don't think the term used, revolutionary, is quite appropriate. So let me clarify that. Now, as far as my career in physics is concerned, I grew up in Indore, and most of my school education and education up to MSc was in Indore. Indore was at that time, it didn't have a university as such. There was a University of Indore, but only for administrative purposes. It didn't have there was no department of physics in Indore. And we had one college, Holkar Science College, which is a very old college, which had, which offered MSc in physics. So I did my BSc and MSc in Indore, and fortunately we had a couple of very good teachers in mathematics and in physics. I won't say that they were very knowledgeable, but at least they were very encouraging, in the sense that if I went and asked them a question, they would not simply say, "Oh, don't worry about it, it's beyond your capacity to understand these high-level, subtle things. You will learn all this later." They always encouraged me and suggested books which I could pursue in order to find answers to my question. Fortunately, at the school level, also we had a couple of very good teachers in mathematics, physics, and one Mr. Ghatole, he was a very good Sanskrit teacher. And so these are the three teachers I can recall from my school days, and a couple of teachers from during my MSc days, who in some sense inspired me to go into physics. After that, after completing my MSc, I was lucky to get into TIFR as a visiting member, and that's where I wanted to do my PhD. But later events, as you would learn in a short while, I did not continue in TIFR. But initial interest in physics came from these couple of teachers at the college, at the MSc level.
So sir, would you consider that you had a natural aptitude for physics or whatever, like maths, or did it naturally come through?
I think it was, let me also make it clear that until my MSc, certainly there was some sort of inclination towards physics and mathematics, um, and it certainly was not influenced. My parents had no influence on these matters. My father was a lawyer, a public prosecutor in Indore, and he let me pursue what I liked. There was no external pressure as such from any quarters. Um, but I must admit that until I finished my MSc and moved on, it wasn't very clear as to what exactly I wanted to do in physics.
Okay, but sir, since you specialize in theoretical physics, was there like why exactly theoretical physics? Like, what are the reasons or what are the factors that one should consider in today's day and age while making the decision between experimental and theoretical?
Well, the decision really came during my TIFR days. So we had coursework in the first year, and after the coursework, students were allocated to various groups, to some extent also depending on their performance. We had the good fortune of having some very outstanding teachers during our coursework. All of them happened to be from the theoretical physics division. One person I would name is Professor Mukunda, a wonderful teacher, one of the finest anywhere in the world, I would say. And he taught us group theory, and I did a project with him. And then we had some lectures by, evening lectures by Professor Balakrishnan. I'm sure that you must have heard of him. He's in IIT Madras. Of course, now he's retired from IIT Madras. He had joined TIFR as a fellow, and he gave us evening lectures on various topics in theoretical physics, orthogonal polynomials, complex variables, and so on. And then there was one Professor A.P. Balachandran, who used to visit, who passed away recently. He was from Syracuse University, and he would also give lectures on various topics in theoretical physics in the evenings. And it is then that it became clear that whatever little aptitude I have for physics, it has to be it is in theoretical physics and nothing else. I was assigned to the bubble chamber group, and I tried for 1 year, tried to get interested in the work they were doing. But somehow, under the influence of these various people, it became clear that I mean, there's no value judgment on what was done in bubble chamber group or was done in experimental groups, and one has to make a conscious and personal decision as to what one would like to be associated with for the rest of your life. So at that time, perhaps under the influence of these great teachers and a kind of an appreciation of my own aptitude and abilities and skills, I felt that theoretical physics was the subject which I would like to pursue later. So after 2 years in TIFR, I felt that it would be, I'll be dishonest to myself if I were to continue in TIFR with a subject with which I did not feel particularly attached. I moved out of TIFR and went to New Zealand, guided by again Professor A.P. Balachandran. I went to New Zealand and did my PhD. and in theoretical physics. So let me complete the story. The person to whom Professor Balachanan asked me to write to was a postdoc in Syracuse for 1 year, and he had finished his PhD in Oxford University in high energy physics. And you know, I'm talking about the 70s. High energy physics was the subject everyone wanted to do. So he felt that it'll be better for me to work with this young man, and was returned to New Zealand. He's looking for students. So you write to him, and so I went to New Zealand because I wrote to him and got a fellowship to work with him for a PhD. For the first 2 years with him, I worked on a problem in Yang-Mills fields, a calculation of neutrino, antineutrino going to 2 photons. And it turned out later, 2 years later, it turned out that that calculation had already been done in astrophysics context. So more or less 2 years of effort, those calculations were a waste. And at that time, I mean, New Zealand was a very remote place with very few theoretical physicists in the country. And one Professor Dan Walls, who had finished his PhD with Professor Glauber at Harvard University, who later on also got the Nobel Prize for his work in quantum optics. He had also joined the department, and he felt that all of us should now work in non-equilibrium phenomena, quantum optics. So it's, I think, a very, perhaps a very unique occasion, that unique event that both the student and the supervisor switched over to working in non-equilibrium phenomena. And my supervisor also worked on non-equilibrium phenomena, Bose-Einstein condensation and so on. Never went back to high energy physics at all. And so later on my work was in high energy, not in high energy physics, but in non-equilibrium phenomena, in chemical kinetics, in quantum optics and so on.
So as we move on further, you have mentioned that you have done your rigorous studies in theoretical physics. So I would like to know more about this mathematical physics in specific, and open quantum system, which you talked about, non-equilibrium phenomena. So could you tell us what is it about, and what exactly do you do with it?
Now, as far as quantum mechanics is concerned, when you deal with a closed system, then the evolution of that quantum system is given by the Schrödinger equation, Schrödinger evolution as we call it. It is a unitary evolution. That means, let me not try and explain the terms involved. I'm sure that those who are listening to me would understand what it means. What it means is that you will have what are called pure states evolving into pure states, mixed states will evolve into mixed states, and there'll be no possibility of, it will not be a very general evolution taking pure states into mixed states, for example. By open quantum systems, we mean that you have a system which is interacting with its environment, and of course the closed system, that is a system of interest plus the environment, they constitute a closed system. They would evolve according to the Schrödinger equation as per the postulates of quantum mechanics. But if you are interested in the system alone, then what you have to do is to, in some sense, reduce the description from the description of the entire system, which is unitary, to the evolution of the system alone. And then you find that the system evolution is no longer unitary. Of course, it takes a state to a state and also allows for the possibility of a pure state evolving into a mixed state, a well-prepared a state about which you have a complete knowledge, then evolving into a statistical mixture of pure states. That becomes possible when you deal with open systems. And dealing with open systems, I mean, it is sort of in some sense, it's a requirement, because if I deal with a closed system, it's always interacting with its environment, so we have to take into account a more general scenario. And particularly of late, in the field of quantum information theory, where you try and see what are the kinds of things that you can do using features peculiar to quantum mechanics that are just not there in classical description, where you want to utilize these descriptions, the quantum description, in order to achieve certain tasks which are either impossible or very difficult in a classical description. You have to deal with the most general quantum mechanical scenario. That is to say, most general state and most general transformation that you can do on a quantum state. And that's where the description of open systems, open quantum systems, that comes in handy and allows you to discuss most general the possibilities. The quantum mechanical description in its most general form has to be used before you can say that you can do better than a classical description. So this theory of open quantum systems, which actually goes back to a lot of work in this direction, was done by Professor E.C.D. Sudarshan. I hope you have heard about him. And he has made very important and significant contributions to open quantum systems. Now it so happened that when I was a postdoc in Germany, in Stuttgart, by chance I happened to look at some work by a Japanese physicist called Shibata. And when you deal with open quantum systems, and you don't speak of a Schrödinger equation, but you speak of a master equation. Now, Shibata and his co-workers, they had they've evolved or written down an evolution equation for open quantum systems, which was different from the master equations which were being used in the context of description of open quantum systems. And in that, their mathematical structure was slightly different. I looked at this equation, and making use of the work of one very famous physicist, Professor N.G. van Kampen, I could decipher or sort of understand the structure of the master equation by Shibata much better. The difference between the two sets of master equations was that at a mathematical level was that one involved a convolution, the other one did not involve a convolution. So this convolution free or convolution less master equation and its structure, mathematical structure, became clear in this work with Shibata. And this particular work that I did in 77 happens to be one of my most cited works. So that is very satisfying that the work that was done immediately after my PhD turns out to be is still very widely cited. The work that I did at my PhD days was on stochastic description of chemical kinetics, and there we invented a technique called the Poisson representation. It is also very well cited and continues to be very cited very frequently, not so much in physics literature, but in biology literature. So there are lots of papers on biological archives which cite this work, where they're talking about cells and DNAs and so on, and how they propagate. And so this work again is has found many applications it seems, in biology. Of course, I did not pursue it much further after my PhD.
So I would like to ask you on, like, when you started your career in theoretical physics. So in the very beginning, what were the challenges that you faced during your early days in theoretical physics?
Challenges, the transition from sort of a provincial town like Indore to TIFR Mumbai. That was difficult because when in Indore, I mean, of course we had I'd studied English and things, physics and mathematics was all done in English medium, but spoken English, we hardly ever spoke English to each other, so there was it was a difficult period in that sense to get to adapt to speaking English as a matter of course. That was first difficulty. Second difficulty was that here, after all, University of Indore was a state university, and there was not so much emphasis on solving problems, and it was a usual kind of a setup that you find in most colleges and universities across the country. So getting used to doing something on your own. So having learned something in electrodynamics or mathematical physics and then solving a problem, that mental resistance because of the way things were taught up to my MSc days, that was a challenge. But I must say that I had some very good colleagues who were from better institutions than the one that I went through, and they were very helpful, and I could just go and discuss things with them. And then this setup, the mental setup of looking at problems and solving it yourself, that I learned in my TIFR days, and that once you begin to accept a given problem as a challenge, making use of whatever you have learned and how to tackle it, then of course things become easier and they help you a lot in your research career later as well.
So, sir, moving on further, would you like to mention a specific problem that you were working on in your early days that you were stuck on for so much time when you solved it?
Yes, there was one such problem, And that happens to be, again, you know, I have always been in favor, never been in favor of purely research institutions. I've always favored institutions where teaching and research go hand in hand. And I was, after finishing my postdoc in Stuttgart, I came back to, now how I came to Hyderabad is a sort of a long story, but let us overlook it for the time being. I came to the University of Hyderabad in 1981. Joined there as a fellow. There was no sanctioned position of a lecturer at that time, sanctioned by the UGC, so I joined on a temporary position. That state of affairs continued for 4 years. Then in between, I got married, had a son, and then the pressure of finding a more secure position became very pressing. So I moved from Hyderabad to the Institute of Mathematical Sciences, where there was a change of directorship. Professor E.C.G. Sudarshan had become the director of the Institute of Mathematical Sciences. I wrote to him and joined the Institute of Mathematical Sciences. I was there for a couple of years, made very good friends, people like Professor Simon, and came in closer contact again with Professor Mukunda, who was at that time in the Center for Theoretical Physics in Bangalore, Theoretical Studies in Bangalore, and was a close collaborator of Professor Simon. So I spent 2 years in Chennai, did some work which is again on the geometric phase, which was at that stage in its infancy, which again that paperwork continues to be cited quite frequently. And then in 87 positions were advertised in Hyderabad at a reader's level, and by that time I had completed the basic requirements to apply for that position. I applied and I moved back to Hyderabad, where I spent 28 years of my professional career until my retirement in 2015. Of course, 2016 January I came here in IISER Bhopal. Now, so there was a fairly long career in an institution which permitted both teaching. You had to teach one course, not like other colleges or universities where you have to spend 2 or 3 hours every day teaching. And there was a good balance between the amount of time that you spent on teaching and your research work. I had an occasion to teach statistical mechanics, and I looked at, when you start teaching quantum statistics, and on the one hand you are exposed to the counting formula given by Bose, and then you are told that in quantum mechanics you have to symmetrize the wave function, and Fermi statistics you have to anti-symmetrize the wave function, and because of the notion of indistinguishability. Now this question always bothered me, and every time I went to the class I was afraid that I had no clear picture of this, and I hope that nobody asked me, what is this? Bose's notion of indistinguishability at a counting level was clear. But what does it mean at a quantum mechanics level? Bose's formula gave a new statistics different from Maxwell-Boltzmann statistics, and that was, as you know, later used by Einstein in order to predict Bose-Einstein statistics. But at that time, quantum mechanics, this is 1924, was in infancy, and there was no Hilbert space or no structure available. That emerged after the work of Dirac, Heisenberg, Pauli, Max Born, and so on, much later. So this question used to bother me, that of course the notion of indistinguishability at Bose's level is clear, and what does it mean at a quantum mechanical level, where to describe a composite system you have to take the tensor product of their Hilbert spaces. What does this indistinguishability mean? So I started looking at this in my own way, and I must have spent 2 years working out specific examples, special cases, to see what is the difference between the classical statistics and the ones that emerge in quantum mechanics if you impose the notion of indistinguishability in a quantum scenario. I was at that stage pursuing this question, and I must, as I said, I must have spent 2 years working out special cases, but there was no clear picture emerging. And then fortunately in our maths department, there were a couple of people who were mathematicians. Normally you find, by and large, mathematicians would dismiss theoretical physicists by saying that you can't even formulate your question properly, we don't understand what the question is, we can't answer we can't find an answer to the question that is bothering you, simply because the question is not precise enough. But we had a couple of people in mathematics, again both of them were from TIFR, and PhDs from TIFR, and were very, very helpful in the sense that they would patiently listen to you and will reformulate your question in a more precise manner and give you advice on what is the mathematical structure that might help you in resolving your question. And I got such a help from Professor Lucili, who was in the maths department, he's no more. He told me that this theory of symmetric functions, symmetric polynomials, is what you need, and I must say that it really helped. It answered my question in a completely general setting in one shot, simply because of this theory of symmetric functions as developed in I.G. MacDonald's book, and all those special cases which I had spent 2 years working on just fell out from the relationship between two possible bases in the space of symmetric homogeneous polynomials, and everything fell into place. Of course, this is not my most cited paper, one of the less cited paper, but that is a work which I feel was very, very satisfying piece of work that I did.
Okay, sir, during early years of research, there are moments of self-doubt or stagnation of your work, or like mental depression or whatever, and that could that leads some people to maybe quit their fields or whatever. But how did you tackle with those problems and went through?
Fortunately, in my case, such a situation, it did not arise because I have most of the work that I've done is in collaboration with my other colleagues in the department. So someone or another would ask a question and we will think about it and pursue it. With the net result that there are a wide variety of topics which I've worked on. It could be quantum optics, open systems, application of group theory, group theoretical methods in physics, geometric phase, statistical mechanics. There has always been something or another. That situation of where one is one finds oneself in a position where you're not making any progress, nothing is happening, you're stagnant, and that somehow fortunately never came in my life.
So as we know, theoretical quantum mechanics in general, or most of theoretical physics in general, needs like a lot of rigorous mathematical work. And has it happened that sometimes maybe like the question that you have, there is no proper mathematical answer to it? And have you ever dealt with any question that even till date does not have a proper answer to it, like mathematically?
No, I would not say that. The sort of mathematics that I have had occasion to use in my work has been something which has been around for hundreds of years. It's not like problems in string theory or quantum gravity, where you are forced to look at mathematics which is evolving, which is very recent. Certain questions in differential geometry which are still being pursued. No, in my case, most of the work that I've done is using conventional mathematics, which has been around for a very long time. It also depends very much on the kind of questions that you try to attack. In my case, my attitude has always been that acquiring knowledge is incremental. That is, you start with what you need, and if that suffices for your purpose, then you don't go any further. You go any further if there are certain questions which remain unanswered and require higher level of mathematics. So I have sort of acquired whatever knowledge of mathematics or physics I had incrementally. So it's not that I learned all of some rigorous, say for example, differential geometry, which is a very interesting subject. I don't know very much, but I know only the basics and only to the extent that I need for my immediate problem. And then work if situation arises where you need to learn a bit more, then you learn a bit more. But in short, answer to your question, no, I have not come across or worked on any problem where the required mathematics was not available.
So, moving on to the next question, I would ask you, like, what is your advice to young people who are going into physics? What topics would you recommend them to be explored that no one has dealt with yet? And how do you see the future of physics?
I think this is again a very difficult question because if I look back and try and analyze my own progress, my own development, most of the things that have happened are sort of the direction which my life has taken is happens to be by accident, it's not by design. I had never thought that I will do theoretical physics until my MSc days, and it just so happened that I met very good teachers in this subject, and only conscious decision which I made was that this is an area for which I have some aptitude, and that it's something which I would like to pursue further because I can only make contributions in this area, and this will give me some degree of satisfaction and some degree of involvement, some degree of participation in that subject. So for me to be able to say, the only thing I would say is that I think this decision as to what you like or what area you would like to pursue is very much should be a personal decision. Once you have made this decision, then after that it is your responsibility to put in the necessary hard work and the necessary commitment, and I'm sure that in due course of time it will bear fruit and it will become an essential part of your life. So what area to choose is very, of course it is also guided to some extent by what is fashionable in the current scenario. Say for example, quantum information theory these days is quite fashionable, and not only fashionable, there's a fair amount of government support as well, interest all over the world, and it's an interesting subject in a sense that very interesting challenges. Having been involved in the West program of the DST, the first initiative on the part of the government to look into the possibilities of applications of quantum mechanics in science and technology, I would say that that is one area where one should, both theoretical and experimental side, there are many challenges, be it quantum computation, quantum communication, cryptography. There are many very interesting areas. So I'm only saying this because I have had some connection with this subject, and it's not to be seen as a value judgment. There are many other areas which are equally interesting, and I think in this regard one has to make a personal decision as to what area inspires you, likes you, you like, and pursue that further. Once you make up your mind, then there should be a firm commitment. This is what I keep telling the students in the class, that once you have decided to take a particular course, then you must go full blast. Take interest in what is going on. Not just do something in order to get a degree. If your heart is not into it, then later on you will find that there's certain emptiness in your life, certain vacancy which no amount of money or position or power can fill. So I think that is all I would like to say on this matter.
Okay, sir. Moving on further, one last question. How do you think has research in physics evolved or like changed ever since you did your PhD back in 1960, was it? So how has it changed in India as well as abroad? Like how has the atmosphere changed?
I would say that the things have changed for the better. That is certainly the way things were taught in our days, where essentially you had to learn, memorize, and you knew what kind of questions which would appear in the examination. There was never any particular incentive for you to solve problems on your own. On that front, things have changed quite considerably. And I think and many new institutions for science, technology have come up where people can pursue what interests them and in a very congenial and good atmosphere. So I think in the last, so my MSc, I finished my MSc in 1970, and since it's almost now 55 years, things have changed enormously for the better. But somehow, this is my personal feeling, that as far as a commitment and passion for among the students towards what is being offered in the courses, I find that students have become, should I say, to use a milder term, worldly wise. So there's certainly not that much passion for what you are doing, for what you are learning, for what is going on in the class. People seem to be more concerned about their, what do you call it? SOP, which was something unknown in our days. That things should look good on your SOP. There's more concern, and I again don't blame them, because in 55 years the social environment has changed considerably, the pressures have increased enormously, the competition has increased enormously. But if you ask me what has changed in the last 55 years, in terms of facilities and institutions, there's enormously more choice available now as compared to in what was available in my days. But again, this element of becoming worldly wise, lack of passion for what you're doing, commitment, I find that is not at the same level as it was in the days when one did not have as many facilities.
Yes, sir. So, and to get into one last question, like as we know, physics in general is a very hard subject to get our head around, and the field, like a research in physics, is very unpredictable, and someone who is getting into physics research has to go through has to be able to face many failures. So, what is your suggestion to someone who would who is going into physics research, and how would you suggest them to deal with failures and maybe keep a calm composure when things don't go their way, and maintain a proper balance between their personal life and research life as well? So how did you handle failures while you were doing your research in physics?
Again, as I said, in my case, again this may be an exceptional case, there were difficulties, ups and downs during the early days in my career, employment. I must have gone to at least after the situation that I described, 4 years in Hyderabad, not getting a permanent position, being married with a child, looking for positions. I must have given interviews in at least 10 different places in India, and certainly was very disheartening to go for an interview and you find that there's not much interest in what you have done, or that the interview is being conducted, you have been asked to appear for the interview only to complete certain formal requirements, that there must be at least 10 people be interviewed, and they had someone already in mind, being asked trivial questions and being dismissed within 10 minutes. So those kinds of things have certainly I had to face them during my career. But after a while, things became very smooth. I have had a very smooth career. And again, it also depends on your attitude. If you are comfortable with your surroundings and you come to equilibrium with your surroundings as quickly as possible, then difficulties don't appear to be difficulties. They seem to be, part of life. So, in my case, again, from my personal perspective, I would say that my life has been very smooth that way. So, as far as whatever difficult period, I won't say difficult, it's a part of that I've seen. I would simply say don't give up. And it has also been my experience that a lot of students whom I've known over this long teaching career who face difficulties, eventually they all settle down to reasonably good jobs which was commensurate with their academic, with their expectations. And so I feel that one should not simply give up. Continue with what you have chosen to be the main the thing that attracts you most in your life. Just stick with it. Eventually, sooner or later, everyone gets a job, reasonably good life, and so this is all I would say.
Sir, outside of research, what hobbies or interests do you pursue to maintain balance, and how do those interests or hobbies feed back into how you do research?
Well, my interests, other than what I do professionally, are in music and Urdu poetry. To interest to the extent that I like listening to poetry. I have interest in languages, so when I was in Germany, I learned a fair amount of German to be able to communicate and to be able to read and understand German. So my interest, and now I would say and I would be 75 in December. After that, I think interest in music and poetry would sort of keep me going. And fortunately, there's plenty of it on YouTube. I mean, you can listen to recordings made in 1965, of great singers of those days, and there's enormous amount of Kavi Sammelan, Mushairas and music available on YouTube. So I think that interest would sort of see me through for the rest of my life, hopefully. And yes, and it's always good to have some interest other than your professional interest, because then you, I think they influence each other in a very significant way and make the interest and your profession, they make them much more effective in that sense.
Okay, sir. To end the interview, we would really like to thank you for giving us your precious time and giving us this opportunity to be able to talk to you. And we are very grateful that you were able to share your life story with us and give us insightful advice on how we can approach physics as a field of research.